Welcome back to AI on AI. Today we're unpacking something every leader should care about: how to make language models not just smarter, but humbler. We're talking calibration, Breer scores, and a new approach called RLCR. Buckle up.
Appreciate the invite. This topic is, the missing piece in the LLM puzzle. We've pushed accuracy hard, but we've sidestepped the "how sure am I" question.
Right, and from a boardroom view, overconfident models are risk multipliers. A wrong but confident answer in a regulatory report can swing an entire compliance audit.
Exactly. In clinical decision support, an hallucinated dose is a showstopper. RLCR intrigues me because it bakes a penalty for misplaced confidence into the training loop.
And it does so with proper scoring rules. Quick refresher, a scoring rule is proper if telling the truth maximizes expected reward. The Breer score is like giving the model a squared slap on the wrist whenever its probability estimate deviates from reality.
Ha, love that image. But contrarian note, penalizing confidence too much can throttle creativity. There's a balance. You want the model to dare, but know when it's bluffing.
Great tension. Let's ground listeners. What exactly happens in RLCR training?
Picture classic RL for language. You roll out a chain of thought. The environment says 1 if correct, 0 otherwise. RLCR augments that with -q-1 squared for correct and -q-0 squared for incorrect, where q is the model's self-declared probability.
Which means two gradients fire simultaneously, one pushing toward factual correctness, the other steering the confidence knob toward calibration. It's like tightening both bolts on a bicycle wheel so it spins true.
And the beauty is you don't need a separate confidence classifier. No extra inference cost. One model, one API hit, two outputs. CFOs love that. Small nuance. The Breer term must be bounded. If you used log loss instead, the unbounded gradient could tempt the model to game the system by outputting 0% sure for everything.
That's the "don't pay someone by the hour if you care about speed" problem. Align incentives or get perverse behavior.
Speaking of incentives, the RLCR paper removed KL regularization during fine-tuning. That was gutsy. Without KL, the policy can drift far from the base model, but they counterbalanced with a format reward to keep outputs parsable.
Yeah, the think, answer analysis, confidence tags are more than cosmetic. They give downstream systems a reliable schema. A knowledge graph team I advise pipes those sections straight into separate storage.
We piloted something similar for a retail chatbot. By weighting ensemble answers with the model's own confidence, we nudged cart abandonment rates down roughly 10%.
That mirrors findings in the paper's confidence-weighted majority vote. When you average confidence across multiple reasoning chains, calibration error dropped measurably. It's classic wisdom of crowds, just trimmed for reliability.
And note the variance analysis. The model's confidence distribution narrowed under RLCR, meaning fewer schizophrenic responses for the same prompt. Consistency is crucial for audit trails.
Let's zoom into the math. Some listeners crave that. How do gradients flow?
Sure, with GRPO or BNPO, you compute advantage A equals R minus B, where R is our combined reward, BA baseline. The calibrated reward packs correctness plus Breer. So you're basically mixing discrete and continuous signals. Gradient variance stays manageable because the Breer term is already squared, bounded between 0 and 1.
And by removing the per-batch standard deviation division in the advantage, they avoided exploding updates on outlier miscalibrations. Smart, practical hack.
Yet someone will ask, doesn't adding a second objective slow convergence? The answer, not really. They saw accuracy equal to RLVR, but calibration improved from 0.37 to 0.3 ECE on Hotpot QA. That's a Pareto win.
Strategically, that unlocks new markets. Insurance underwriting models can finally say, I'm 40% sure this claim is fraudulent. Actuaries can price uncertainty explicitly instead of reverse engineering it. In Philosophy of Science, Karl Popper said, our knowledge can only be finite, while our ignorance must necessarily be infinite. RLCR makes the model admit that.
Love the quote. Any war stories?
We deployed a prototype on radiology report summarization. Pre-RLCR, the model hallucinated cis dimensions about 12% of time with high confidence. Post-RLCR, same hallucination rate, but confidence on wrong summaries cratered, down to around 0.2. Radiologists could triage instantly.
I saw the flip side. On an arithmetic dataset, the base model would spit 100% confidence even after guessing. RLCR forced it to dial down to 30 to 40% when uncertain, which actually let downstream heuristics request a second pass, boosting total accuracy.
Here's my curveball. I think we're missing the real bottleneck: calibration across time. Models drift after deployment. A Breyer-based objective helps day one, but without continual reinforcement, tomorrow's distribution shift could wreck calibration again.
Fair, ongoing fine-tuning or online learning might be needed. Similarly to how an e-commerce search engine re-ranks daily, we might schedule RLCR refresh cycles tied to key metrics. There's a heuristic. Calibration decays proportional to domain shift. If the environment changes 20%, expect ECE to rise roughly the same unless you adapt.
Terrific. Let's quickly contrast post-hoc calibration. Why not just train a probe?
2 reasons. First, probes add inference latency. Every millisecond counts in real-time bidding. Second, probes often overfit the training domain. RLCR bakes robustness into the shared representation.
Plus, small probes lack capacity to pass chain of thought. The paper showed that at 0.5 to B parameters, analysis-informed classifiers beat vanilla confidence probes handily.
And from budgeting standpoint, 2 models doubles hosting cost. RLCR is 0.1 extra parameters, just the tokens needed for the confidence scaler.
We're nearing wrap-up. I'd like each of you to offer one actionable takeaway for listeners.
If you care about trust, treat confidence as a first-class citizen during training, not an afterthought.
Technically, start with a proper scoring rule that's bounded. Breer is simple and effective.
Operationally, instrument your pipelines to utilize verbalized confidence. Don't let that scaler go unused.
Strategically, measure calibration KPIs alongside accuracy. Your shareholders will thank you for reduced risk exposure.
And watch deployment drift. Plan periodic RLCR fine-tunes, or your model's humility will fade faster than you think.
Fantastic. To borrow Einstein's line, science is the refinement of everyday thinking. Today we learned that refining a model's uncertainty may matter as much as refining its answers. Thanks to all our experts, and thanks to you for tuning in. Until next time, stay curious and calibrated. Welcome back for Part 2, our Under the Hood segment, where we translate white paper diagrams into engineering tickets and boardroom roadmaps.
Let's kick off with the plumbing. RLCR slots neatly into a standard PPO or GRPO loop. Same replay buffers, same advantage estimates. The only delta is that reward function combines the 0-1 correctness bit with a Breyer term.
Right, and for code folks, in PyTorch you'd compute reward equals correct.float. 2. Drop that into the advantages tensor, and boom, you're optimizing calibration. No new heads, no structural change to the model.
A critical implementation nuance is bounding. Because the Breyer score maxes at 1, we sidestep gradient explosions. If you're tempted to use log loss, you'll need clipping or you'll nuke stability when Q0. From a CTO angle, the bounded reward means predictable GPU utilization. No surprise spikes in loss that stall training runs or blow through your cloud budget.
Quick reminder, they also ditched KL regularization. Instead, they rely on format rewards, those XML-ish tags, to constrain drift. That saves you from tuning a fragile KL beta hyperparameter.
Absolutely, but watch out for reward hacking. We saw a toy model that learned to spit Q equals 0.5 for everything. Technically well calibrated, but strategically useless. Their fix was to give the correctness term equal weight, forcing the network to keep chasing accuracy.
Speaking of accuracy, the paper warmed up math models with a tiny supervised phase, only 500 examples, to teach the network how to talk about uncertainty before RL. It's basically few-shot humility priming.
And that priming matters. Without it, the analysis text tended to be generic. There might be ambiguity, which carries little signal for small probes. With SFT warm-up, the model cites concrete steps. Integration by parts may miscopy the minus sign, which a classifier can latch onto. Translating to business value, richer analyses let compliance teams create rule-based triggers. If the model mentions ambiguous jurisdiction, route to a human. That's a straight-line reduction in legal exposure.
Love it. Let's dig into data engineering. How did they prep Hotpot QA Modified?
They purposely removed varying amounts of evidence to stress test uncertainty. Implementation-wise, that's a simple pre-processing script. Randomly drop key paragraphs with 0, 1, 2 probabilities and cache which ground truth hops were deleted.
And here's the surprise insight. By feeding uncertainty during training, the model got better at cross-domain calibration without ever seeing those other domains. That hints at a representation that factors evidence sufficiency, a transferable feature.
On the infrastructure side, we stored think, answer, analysis, and confidence in separate BigQuery columns. Analysts can SQL filter, confidence 0.4, and auto-escalate. Dead simple ops.
For online serving, we appended one extra token to the generation budget. The scalar Q token plus delimiter adds negligible latency, sub-millisecond under TensorRT-LLM. And when we ensemble, we use a confidence-weighted majority vote. Implementation trick. Compute softmax over confidences to normalize, then use that as weights. Effectively a differentiable selection if you want gradient-based re-ranking down the line.
Many execs ask, can I retrofit RLCR onto an existing RLHF model?
Short answer, yes. Freeze everything except policy weights. Run a few hundred RLCR epochs. Think of it as a calibration top-up, like rotating tires, not replacing the engine.
I'll be contrarian here. If your original reward model was itself overconfident, retrofitting may inherit bias. You might need to reannotate a sliver of data with human confidence gold labels to anchor the Breer term.
True, but even 5% of your original dataset suffices. The 80-20 rule applies. Most of the calibration gain comes from the tail cases where the model used to be certain and wrong.
On monitoring, we track ECE and AROC weekly. Rule of thumb, if ECE drifts more than 25% relative, schedule a mini-batch RLCR refresh. Continuous integration for calibration, if you will. Business case time. An international bank piloted RLCR for KYC document vetting. Calibrated confidence let them auto-approve low-risk docs while flagging the 15% ambiguous ones. Turnaround time dropped sharply, and auditors praised the explicit uncertainty trail.
Another example, an e-commerce search engine now suppresses zero-confidence enrichment snippets to avoid mismatched product specs. Customer trust scores nudged up a few points.
Folks, we're nearly out of tape. Lightning round. Biggest implementation pitfall.
Neglecting to clamp Q between 0 and 1 during training sounds trivial, but I've seen gradients explode because someone forgot a sigmoid.
Forgetting to weight format reward high enough, you'll end up parsing jungle text.
Skipping evaluation on out-of-distribution sets. You might be calibrated on math, but cocky on trivia.
And on the business side, if you don't surface the confidence to end users in UX, you leave value on the table.
Lastly, remember the Eisenhower maxim. Plans are worthless, but planning is everything. Build calibration into the plan. The exact numbers will shift, but the process endures.
Perfect finish. Calibration isn't a feature, it's a discipline. Thanks to all our experts for the tour of the engine room. Listeners, test your models and test their humility. Until next episode, keep your AI both smart and self-aware. Before we hit stop, let's stitch the tapestry together. What did we actually learn today in one coherent storyline?
From the strategy chair, the headline is simple. Calibrated confidence converts AI from a flashy gadget into a dependable co-pilot. Whether that's triaging KYC forms or flagging shelf descriptions, predictable uncertainty unlocks automated decisions without nuking brand trust.
Technically, the killer move was fusing a bounded proper scoring rule, the Breyer term, with the classic binary reward. That preserves gradient sanity while guaranteeing that the optimal policy is both accurate and honest about its odds.
We also saw that a microdose of supervision, just 500 annotated uncertainty analyses, can prime the network to generate actionable self-critiques, which smaller probes can then leverage. Think of it as seeding a crystal lattice before full-scale growth.
Don't forget the operational heuristic. Confidence is a first-class feature. Surface it in analytics dashboards, pipe it into routing logic, and monitor ECE drift just like you track latency. Otherwise, you're buying a sports car and never leaving the driveway.
My closing contrarian riff. Everyone obsesses over model size, yet today proved that reward design moves the needle more than adding another billion parameters. Optimizing the objective you actually care about beats brute force scaling every day of the week.
Amen to that. So to recap, one-line code change, bounded reward, light SFT warm-up, continuous calibration monitoring, and a UX that respects uncertainty. Implement those, and you're not just shipping answers, you're shipping trustworthy judgment. Thanks for tuning in. Keep iterating responsibly, and we'll catch you on the next episode of AI on AI.